Chapter 2 should just be a review of cell structure and function. And we're going to start with looking at just a chemistry review in this lecture. So if you remember from chemistry, atoms are the smallest unit of an element that still retains the element's properties. And remember that atoms are composed of 3 subatomic particles. So remember they're composed of protons with a positive charge and neutrons with no charge, and they're located in the nucleus of the atom. And then we have electrons with a negative charge that are zipping around the outside here. So that makes up the atom. And then if you put 2 or more atoms together and bind them together with covalent bonds, that'll form a molecule. And then if you put a bunch of molecules together, then you can form a cell, which remember that's our smallest unit of life. And then the 4 most common atoms in the body, if you remember from chemistry, that would be hydrogen, oxygen, nitrogen, and carbon. So I always just remember hunk with a C. So not a K, but with a C. And then the most common molecule in the body, and a big hint, it's the most abundant fluid in the body, that would be water. So the most common molecule in the body would be water. Okay, let's just review some of the chemical bonds. So we're just going to take a look at 3 of them. We'll look at covalent bonds, hydrogen bonds, and ionic bonds. So remember covalent bonds. That's where the 2 atoms are going to be sharing electrons between them. So we have 2 different types of covalent bonds. We have nonpolar covalent bonds and polar covalent bonds. In nonpolar covalent bonds, the electrons are going to be shared equally between the 2 atoms. So like for example, we have carbon dioxide pictured over there on the right, and the atoms being shared between the carbon and the oxygen atoms will spend equal amount of time between both the carbon and the oxygen atoms. So there's not going to be any charges anywhere on the carbon or the oxygen atoms at all. So that's going to make these nonpolar covalent bonds. That'll make the molecule hydrophobic because there's no partial charges, full charges, no charges anywhere. So hydrophobic, remember that means it's afraid of water, it doesn't like to mix with water, so it'll just huddle by itself and doesn't want to mix with water at all. And then polar covalent bonds are very different because the electrons are going to be shared unequally between the 2 atoms. So what happens is one of the atoms is going to be much more electronegative than the other one. So for example, in water, the oxygen is much more electronegative than the hydrogen atom. So that just means that oxygen is a big electron hog. It loves electrons and wants to spend more time with them, and so it really pulls on those electrons. Electrons spend a lot more time around the oxygen atom than they do around the hydrogen atoms. So the oxygen ends up with a partial negative charge on its end, and the hydrogen atom ends up with a partial positive charge on its end because the electrons aren't spending as much time there. So with a polar covalent bond, you end up with 2 poles on the molecule. One pole will have a partial negative charge, and then the other end, the other pole will have a partial positive charge. So that's how we got the name polar covalent bond. And because we've got these partial charges on these polar molecules, that makes the polar molecule hydrophilic. Phil means to love. And so these polar molecules love water. They love to mix with water because water molecules, obviously being polar molecules, have partial charges and they like other polar molecules, so they all like to mix together. Okay, our next type of chemical bond are hydrogen bonds. So hydrogen bonds are going to form between 2 polar molecules. So So that would be important to get the big picture here. And you can see that we've got some water molecules in this picture. And here's one water molecule up here on top, and then we've got another one below here. And what's holding the water molecules together, these straight lines here, those are representing polar covalent bonds. And notice that we've got unequal sharing of the electrons between the hydrogen and the oxygen atoms because we've got the partial positive and partial negative charge there. So we know this is a polar covalent bond. So that makes this water molecule a polar molecule. And then we've got another polar molecule down below with another water molecule. And what happens with forming a hydrogen bond is we get an attraction between the partial negative charge on one polar molecule and the partial positive charge on the other polar molecule. So those two attract each other. And so this dotted line in between these two polar molecules, that's a hydrogen bond. Okay, so it's just this attraction between these two polar molecules, between the partial negative and the partial positive charges between the two polar molecules. So that's a hydrogen bond. The reason that there's a dotted line there instead of a solid line is because hydrogen bonds are pretty weak. They're easy to break. Whereas the covalent bonds, because they're actually sharing the electrons, they're a lot harder to break. It requires a lot more energy, and so there's a solid line there, just indicating they're much harder to break. Okay, ions. We have two different types of ions depending on whether the atom has gained or lost electrons. So an anion has gained one or more electrons. So it's going to end up with a negative charge. So an anion will have a negative charge. And it has gained one or more electrons, and that's where that negative charge comes from. And then a cation has a positive charge. And that's because it's lost one or more electrons. Okay, and so the way I keep these two words straight, the only way I can do this is I just remember cation has a T in the middle and the T looks like a plus sign. And that's how I remember a cation is a positively charged ion. So an example of a cation would be maybe like a sodium ion. Okay, it has a plus charge. An example of an anion would be maybe a chloride ion. Okay, with the negative charge. Okay, that would be an anion. And what happens when an anion and a cation get close to each other, because they've got a full charge, they don't have a partial charge at all because they're not unequally sharing electrons at all. They've just lost or gained the electron. So what happens is they're going to have an attraction between that full positive and that full negative charge, and they're going to form an ionic bond between the anion and the cation. Okay, and that'll form the ionic bond. So ionic bonds are going to be pretty strong. So if you think about like salt, like a salt crystal, that's pretty hard to crush a salt crystal between your fingers because of those ionic bonds there. But if you put the salt into water, the ionic bond is very weak in water, and we'll look at a picture and it actually will break and dissolve in the water. And then also in physiology, because we are dealing with the body and we have lots of water inside of our body and inside the cells, when we have ions that are dissolved in water, they form these electrolytes. Okay, and you might have heard that, if you're working in a lab or a clinic and they're talking about electrolytes, you're like, what is that? They're just talking about these ions dissolved in water. And they can conduct an electric current. So that's how they got the name electrolyte. Okay, so there's lots of examples of electrolytes that you can measure in a person's blood, like their potassium levels, sodium, chloride levels, calcium levels. So any of these ions that are dissolved in your blood, in the water like that, those are all your electrolytes. Okay. All right, so ions. Do you think they're going to be hydrophilic or hydrophobic? Would they like to mix with the water? Remember that water is a polar molecule. It's held together by those polar covalent bonds. Water has a partial negative and partial positive charge on it. So ions are going to be hydrophilic, okay, because they have a full charge, and water is going to be very attracted to the charge on those ions because water has the partial charge on them. So the ions are going to mix very well with the water, dissolve, and they like being with the water. Okay, so here's just some examples of ions and ionic bonds. So here we have a sodium atom up here at the top, and it's going to lose an electron here and becomes a positively charged cation here, the sodium ion. And then here's a chlorine atom, and it's gained an electron here from the sodium, and now it becomes an anion, has a negative charge, and now it's a chlorine ion. And when those two get close to each other, they will form ionic bonds between each other, which are pretty strong as long as water is not around, and they'll form the salt crystals. But if you throw the salt into water, the water will be very attracted to the full charge on the chlorine and the sodium ions, and they will break the ionic bonds between them and separate the ions from each other, and the salt will dissolve in the water. So ionic bonds are strong unless water's around, and then the ionic bonds will break apart. Okay, so this is really important to know because this will come back again later when we talk about membrane transport. So you need to know what can cross the membrane and what can't. So it's important to know what's hydrophobic and what's hydrophilic. So nonpolar molecules, so things that are atoms that are sharing their electrons equally, so they have no charges anywhere, no partial charges, no full charges, nothing, they're going to be hydrophobic. So examples of nonpolar molecules would be things like oxygen, carbon dioxide, any of your lipids. Okay, they're all going to be nonpolar. So if you look at your plasma membrane, remember that the plasma membrane is made up of a phospholipid bilayer, and remember these phospholipids have these fatty acid tails sticking off the heads here. And remember those fatty acid tails are hydrophobic. They don't like to be around the water, and so they will huddle in the middle here and form this hydrophobic layer in the middle of the cell membrane, and that forms a barrier. But if you're a nonpolar hydrophobic molecule like oxygen, well, you can just diffuse right through that plasma membrane, no problem. Okay, so it'll just diffuse right through. So these hydrophobic nonpolar molecules, yes, they can diffuse right through the membrane, not a problem. Okay, but what about hydrophilic molecules? Things that like to mix with the water. So these would be the polar molecules. They have partial charges on them. So something like glucose, for example, or ions. Maybe you have like a sodium ion or a chloride ion. So these will have, like the polar molecules have the partial charges on them, or the ions have like a full charge. So if they are sitting here, maybe you've got, for example, maybe you've got a potassium ion here, or maybe you've got some glucose, okay, which is a polar molecule and would have some partial positive and partial negative charges on it. So if they're sitting on one side of the membrane or the other, they're going to get stopped by this middle part of the plasma membrane that's hydrophobic. Okay, because the glucose and the ions here, these polar molecules and ions, they're hydrophilic. And they don't like hydrophobic stuff, and hydrophobic things don't like hydrophilic things, and they don't mix very well. So they're not going to be able to diffuse through the membrane. Okay, so they're going to need a transport protein to get across the cell membrane. So no, they cannot just diffuse through. They would need the help of a transport protein to get across. Okay, just some more chemistry terms. Remember, a solution is just a mixture of a solute that's dissolved in a solvent. So the solvent is the thing that's doing the dissolving. So in our bodies, our big solvent would be water. So that would answer our question here. The most important solvent in the body is water. And then the solute is whatever is being dissolved. So maybe it's salt or glucose. It could be a number of different things that get dissolved in the solvent or the water. And then we oftentimes like to measure the concentration of a solution. So that's going to be measured by taking the quantity or the amount of the solute, and then you just divide that by the volume of the total amount of the solution. And a lot of times we'll measure that in molar, and that's just defined as 1 mole of the solute dissolved in 1 liter of solution. Okay, so a 1 molar solution is, the units would be 1 mole of solute per liter of solution. And then a lot of times our amounts are going to be a lot smaller. So maybe the quantity of the solute is a lot smaller. So maybe we have a millimolar concentration. So milli, remember, means 1,000th. So we're just going to divide that number by 1,000. So we'd have 0.001 molar solution. Okay. So, and we'll see some of these numbers later on as we go through. We also need to review acids, bases, and pH because that's going to be really important later on. So remember that a small amount of water will dissociate or fall apart into hydroxide ions and hydrogen ions. And remember that hydrogen ions are the same thing as protons. So acids, when you put them into water, will release hydrogen ions. So here we have hydrochloric acid, which is the same thing as our stomach acid. And when it gets put into water, it releases hydrogen ions. So that makes it an acid. And then bases will do the opposite. So when you throw them into water, this base, the R is just the rest of whatever the molecule is. So maybe this is a protein here with this amino group on here. And when we put this into water, it will accept or remove the hydrogen ions, because when you go on to the other side, what you end up with, you can see that the hydrogen ion is now gone. Okay, it has now attached itself to this protein and it's disappeared. So bases are going to accept or remove hydrogen ions and get rid of them. So pH, the formula for that, it's the negative log of the concentration of the hydrogen ions. And if you look at the formula for pH, the reason there's a big H in pH is because pH is measuring the hydrogen ion concentration. So that's how you remember what pH is measuring. Okay, so pH measures the concentration of hydrogen ions. So this bracket, that just represents the concentration. So it's just the concentration of the hydrogen ions. Okay, and so for example, like in this chemical reaction here with looking at distilled pure water, and the concentration of the hydrogen ions in distilled water is 10 to the minus 7th molar of hydrogen ions. And you just plug in that concentration of hydrogen ions into your pH formula. It's really easy to calculate pH because all you do is you just take the minus sign, that cancels out the minus sign there in the exponent, and then the log will cancel out that base 10. And so all you do when you calculate pH is you just look at that exponent, and whatever that number is, that's your pH. So the pH would be 7, which is neutral. So here's our pH scale. A pH of 7 is neutral, meaning that you have an equal number of hydrogen ions and hydroxide ions in the solution. So this would be pure water here in the middle. But as the pH number gets smaller, so as you decrease down to 0, you get more and more hydrogen ions and you get more and more acidic. And the way that the scale is, it's a log scale. So as you go down in number, it's a factor of 10. So for example, if you take a look at maybe tomatoes at a pH of 4, and maybe you're looking at pickles, pH of 3, the pickles at a pH of 3 are 10 times more acidic than the tomatoes at a pH of 4. Okay, and then if you were to compare the pickles to the stomach acid at a pH of 1, so 1 versus 3, there's 2 units there, C of 10 times 10. So the stomach acid is going to be 100 times more acidic than the pickles would be. Okay, so that's how the scale works. And then if you go from a pH of 7 and your number is getting higher than 7, then you're getting less hydrogen ions and your pH is getting more basic or alkaline. Okay, buffers are really important in the body. We're going to be talking about some buffer systems later on as well. I like to think of buffers as sponges. So they're there to soak up extra hydrogen ions if you have too many, or if you don't have enough, you can squeeze the buffer sponge and release the hydrogen ions. And they're there to make sure that the pH stays within the normal range, because it's very, very important that your pH stays within a very narrow normal range, because you've got to keep your blood pH within homeostasis, because if you get outside of that, you will get sick, and if you keep going beyond that, then it will kill you. Let's just take a look at an example of a buffer system in the blood, and we're going to be working with this more later on this semester, so we'll just kind of introduce it here and just kind of get you used to working with this and thinking about this, and we'll come back to this later though. So let's just do some examples here. So with this equation, we're just going to ignore the carbon dioxide and the water for right now. So we'll come back and work with that later, because your respiratory system actually affects your blood pH, which is kind of interesting to think about. Okay. All right, but let's just kind of focus on the rest of this with the carbonic acid and the hydrogen ion and the bicarbonate ion over there. Okay, so let's say that your blood pH increases. Okay, so your pH is going to increase. And if we think about that, what happens to the amount of hydrogen ions? So your hydrogen ions, if your pH number is getting bigger, that means that you're getting more alkaline or basic. So that means you have less hydrogen ions. Okay. And the body's looking at that and says, hey, we're getting out of the normal range. My blood pH is getting too basic. So we need to do something with our buffer system here and get us back to the normal range. Okay, so our problem is we don't have enough hydrogen ions. They're too low. So which way do we want to make this reaction go to increase our hydrogen ions? So what I did on the bottom here is I rewrote this just so we could look at it again. And so we could either make this reaction go to the right, which means that we would take the carbonic acid and then it would fall apart and make more hydrogen ions in this bicarbonate ion. Or we could make it go to the left and then we'd end up over here and then there'd be no hydrogen ions over there. Okay, so which way would you want to go? Would you want to go to the right and make some hydrogen ions and end up over here? Or would you want to go to the left and end up over here and the hydrogen ions would be gone? Well, our problem is we don't have enough hydrogen ions and we need to make some more. So we want to go to the right because we want to make more hydrogen ions. Okay, so that's what we're going to do. Okay, so we're going to go to the right. Okay. All right, and let's do one more example. So let's say that we've got the opposite problem. Let's say our blood pH decreases. So that means our pH number is getting smaller. Okay, so if your blood pH decreases, so the number is getting smaller, that means we're getting more acidic. So we're going down the scale, and that means we're getting more hydrogen ions. So it's always the opposite of what your brain thinks it should be. Okay, it is for me. So our problem is we've got too many hydrogen ions. Okay, and which way do we need to go to get rid of those extra hydrogen ions? Okay. So if we look at our reaction here, we could go to the right, and if we went to the right, we'd end up making more hydrogen ions. Well, that would not be good, because our problem is we got way too many hydrogen ions. But if we went to the left, and we end up over here, well, the hydrogen ions are gone. Well, that's the way we want to go. Okay, because we want to get rid of those extra hydrogen ions, and so we're going to go to the left on that. So the answer on this one will go to the left. So we'll go the opposite direction to decrease the hydrogen ions to get to normal. Okay. All right, and I know this is a little bit confusing. So if you're having trouble with this, please let me know and I'm happy to help you with this. And we're going to come back to this later in the semester and do this again. Okay, so it will reappear. Don't just like, oh, I don't get this. You know, I'll never see this again. Yes, you will. Okay, so it's better to understand it now, because it'll make things easier later on in the semester. So if you're having trouble with this, just let me know and I'm happy to help you with this, okay? So just let me know and happy to meet with you, okay?